In this work, we use a simple and suitable atomic finite element model capable to describe the different interactions between atoms and predict the elastic properties of carbon nanotube. Also, the effect of carbon nanotube geometry and on the Young's modulus is investigated. The obtained result showed that our method is fast and gives acceptable accuracy for predicting the elastic properties of carbon nanotube. Due to the attracted properties of carbon nanotube, especially the mechanical properties, several researchers studied this material by using different techniques. Among these researchers, Gledal et al. 23 developed a special and finite element method at the atomic scale based on harmonic potential and predict the mechanical properties of biodegradable polymer. His result is good and showed an important result. Our work is based on Gledal's work in order to predict the elastic properties of carbon nanotube. The present atomic finite element based on the potential described by three terms. UB is the stretching term between two atoms, describe the axial deformation. U theta bending angle term between three atoms and describe the flexion deformation. U tau torsion angle term between four atoms and describe the torsional deformation. The adequate model used is of three types. The stretching element, like spring between two atoms, describe the axial deformation. The element stiffness matrix of this element is 6 by 6 of size and contain alpha I coefficient, which is depend on the atomic coordinate. The bending angle element is defined by three atoms and describe the flexion effect. Its stiffness matrix is 9 by 9. The torsional element defined by four atoms and describe the torsion about the bond. Its element stiffness matrix is contained of 12 by 12 coefficient. In order to check the accuracy of our method, it's compared with literature in table 2. There is a good agreement between our method and those of AFEM 21 and SPFEM 27 for the Young's modulus. Also, the Poisson's ratio predicted by our method agree well with the literature. On the other hand, the effect of length to diameter ratio, diameter and chirality of the carbon nanotube is also studied. Our results are compared with Liu et al. Work and showed in figures 5 and 6. From this figure, we see that our model is underestimate the Young's modulus compared to Liu. In figure 5, we see that L to D ratio have not significant effect on Young's modulus for both chirality. In figure 6, the Young's modulus of zigzag and chiral carbon nanotube is affected by the diameter change, especially at small values, whereas the armature is less affected by carbon nanotube diameter. The torsional element proved that to contribute to stabilize the system and give a good result. Donc, in conclusion, in our work we have used a special atomic finite element based on harmonic potential in order to predict the elastic properties of carbon nanotube. Our results are compared with the literature and show the good accuracy. The effect of length to diameter ratio, the chirality and the torsional element on the elastic properties is also studied by the present method. The obtained result showed that our method can be used to study the mechanical behavior of carbon nanotube rapidly with a good accuracy. Thank you for attention.